Okay. This has really been a wonderful conference with many, many great talks, both in these plenary sessions and in the parallel sessions. I will thank the organizers towards the end, but let me start by not thanking them for asking me to give this visions talk. Luckily, they didn't ask me to summarize this conference because it's clearly, or at least for me, unsummarizable. So I'm glad I don't have to attempt to do that. Really has been an amazing time here in China, in Beijing, in Tsinghua, which is a beautiful campus. And I will try to entertain you at the end of this long week with so much information that I'm sure you're all, as I am, mentally exhausted. And so I hope my talk will be slightly entertainment, will contain a little bit of history, and a little bit of vision, hopefully. But first I'd like to say a bit about China. You know, I noticed in the news a few days ago, actually here, an incredible development in China, which as an American I'm very jealous of. And, oops, this, oh, I know it. I forgot to connect it. That's here. Okay, that should work. So the news was this picture on the internet, which only took me 10 or 15 minutes to download. So what is this strange contraption? China has built the much anticipated straddling bus. This is actually a model that was shown off in May, but they've actually built the real thing. What it is this is a bus which travels along a path like this, and it's powered by electricity, no pollution. It transports 1,400 people in this bus, 40 miles an hour down urban streets, and cars can pass right through it. So it's no barrier to traffic, no pollution, mass transportation. You know, I encounter LA traffic all the time, or New York traffic. This was invented in the United States in the 60s. It was planned for New York. They've built it. And it was taken for its first test drive on Tuesday in the northeastern city of Tsinghua. Now, I noticed this, it's amazing, but I was especially drawn to the fact that Tsinghua, correct, is the site of the Great Collider. Now, the Great Collider we heard a bit about in the first day from Yifang. And it is a marvelous project that is being proposed here in China in collaboration with the international community in high energy physics. I am convinced that it would be a great boom for China and for international collaboration and for physics and for science in general. And this might not be the site, but this is one of the proposed sites. I hope you all agree with me. I was going to do a little experiment. If you believe that the collider is a great idea, can we clap for the collider? Okay, that's pretty good. Oops. So, Strings 2016. So this was a wonderful conference, as strings tend to be. But one of the things characteristic about this conference was the incredible variety and breadth of topics discussed, which is either a sign of great health and vitality or a sign of lack of focus. I think it's the former. Now, as I said, the conference as a whole is not summarizable, certainly by me, but there are two particular developments which were discussed at length by a variety of speakers, which I personally thought were particularly exciting and new. And one, of course, was the increasing understanding of the emergence of space-time and the relationship between quantum states, and in particular the entanglement of quantum states in space-time geometry. And the other was somewhat newer in a sense, the SYK model, perhaps a soluble holographic string theory. And many other areas in which string theory is exploring. I think I've covered a good portion of them, but there actually are others as well. Now, I don't have either the time or the preparation or probably the ability to comment on each of the developments. And I plan to revisit the website when I get back to Santa Barbara, because I've learned, and I'm sure we all have, a lot this last week. But in these particular topics I find particularly exciting. Emergent space-time has always been a dream and a goal of many of us in string theory, and it's now been realized for some years how powerful is the use of entanglement to relate the quantum states of a dual description of string theory to the structure of space-time itself. Juan Modestina gave a beautiful review of this subject, and there were many other very wonderful contributions to this connection between the structure of quantum states on the boundary of ADS and the geometry of the bulk. I think we understand now in greater and greater detail how the nature, or beginning to, how the structure of semi-classical space-time in the bulk is determined by the nature of quantum states on the boundary. One of the main tools being the Ryu-Takanaki conjecture formula, relationship between entanglement on the boundary and the geometrical properties of a minimal surface in the bulk. One of the contributions, and I'm not really going to refer to any particular contributions in this talk, but the one of them that I found most interesting was that of Matthew Hedrick, who replaced this way of thinking about the, or of calculating the entropy of a subsystem on the boundary in terms not of the area of a minimal surface, whose boundary is that region in the bulk, but rather the minimal density of threads passing from a region A to its complement. And to some extent, that addressed the question that Juan ended his beautiful review with: where are the bits in the bulk? So if the ADS-CFT duality is a relationship between the quantum structure of states on the boundary and the bulk, where do the qubits that one can see on the boundary exist in the bulk? Matt seems to have replaced that by the question, what are the threads? And these flow lines, the threads, beg the question, what is flowing? But replacing one question for which we don't know the answer with another, although it might not answer the question, I have no doubt is going to shed new light on emergent space-time. The other thing which is very new and exciting, in my opinion, is the SACHDEV-YE KITAEV model. A model that was developed many years ago in condensed matter physics in order to find a quantum critical point, a conformal field theory, in a simple quantum mechanical soluble example by Subir SACHDEV-YE, and used by KITAEV to perhaps construct a simple holographic dual of a black hole or of quantum gravity. Now, KITAEV is somewhat like Perlman. You know, he doesn't publish. So he does very interesting physics, but it's very rare that you find it in print. If you want to learn about the origin of this model, and there's a set of beautiful lectures on the KITP website that were given a while ago. And many people, Mary and Polchinski and Rosenhaus, and especially Stanford and Maldacena and Verlinde and many others, have been explaining and filling in the gaps and going beyond what KITAEV announced in this talk, somewhat like the way the response to Perlman's proof of the Poincare conjecture. So this is a fascinating model. It is perhaps the first of a new class of large N theories. And for some of us, large N has been a lifelong obsession. Vector large N theories are simple and have given us enormous insight into many-body theory and quantum field theory, as have matrix large N theories. And this kind of large N theory is somewhere in between, soluble but richer than vector models. And it might be, for all I know, just the tip of the iceberg on a whole class of large N soluble theories. It is an amazing example of a one-dimensional system, or just quantum mechanics with no space, with a diffeomorphism invariant conformal symmetry, infinite dimensional conformal symmetry in the infrared. That's of course broken, but that's quite an amazingly simple infinite dimensional gate symmetry. And most excitingly, it might be a soluble holographic that V should be a C, string in the bulk. And soluble models, even in 1+1 dimension, or maybe there are more dimensions, have always proved in our field to be of enormous value. So this model and its elaborations and variations might give us much insight in the future. Now, the conference started out with a wonderful talk by John Swartz on the history of string theory, and at least the history in the 20th century. And then there were some 21st century attempts by Nima and by Zohar to redo history. So I would like to make some historical remarks, and I planned them actually in order to say a word or two about one of the great physicists of the last century, who contributed much to string theory, Stanley Mandelstam, who died a few weeks ago. Now, Stanley was, in my opinion, the godfather, and I don't mean the mafia godfather. I mean, you know, he gave birth, in some sense, to string theory, which I'll explain because I was around. And aside from John, I think that's, we're unique in that capacity here. So the intellectual history of string theory actually does go back 50 years, just about. It is half a century. And it goes back to the early 60s, to the middle 60s, the period of 1965, 67, when the rage was current algebra sum rules. You know, trying to test the broken chiral SU3 cos SU3 flavor, symmetry, as we would say nowadays, of the strong interactions by writing down sum rules. And so you had these sum rules, and a variety of people figured out how you might test them, calculate both sides of the sum rule. And typically, the only theoretical method that poor theory had back then was to sum over poles. That was about it. You know, if you tried to have a theory of the S matrix of a scattering amplitude, you just figured out what poles exist in say, the direct channel, and you summed over them. It's the limit, how far we've come in half a century. Okay, you summed over poles. In terms of stringy diagrams, we would say nowadays you summed over poles in this channel. Two particles come in, resonance. You put into your sum rules that enabled you to check these sum rules that follow from current algebra, a sum of poles, and you tested the sum rules. But there was another development in the early 60s, which had to do not with direct production of resonances, but rather exchange of REGGE trajectories, especially as it was these straight line REGGE trajectories that described the analytic continuation and angular momentum of the partial waves in cross channels, in the T channel, were discovered to lie on these linear trajectories. And another approach to discussing amplitudes, especially at large energy, was to sum over the exchange of REGGE poles or REGGE trajectories. Now, at some point, Dolen, Horn, Schmidt, and Iggi noted what we now call a duality, and as far as I know, this was the first time duality appeared, the word and the notion, in high energy physics. They said instead of summing both over resonances and exchange of REGGE trajectories, which was natural to do, that was double counting. And their duality was a kind of vague statement that one should represent scattering amplitudes as either sums over resonances in one channel or trajectories in the other channel. Pretty weird thing. Of course, not the string theorists, where these are simply different ways of cutting, piecing together the same stringy diagram. But there was no string theory back then. However, this had some testable predictions. You could test it. You could take a scattering amplitude that you measured, try to estimate it using a sum of poles in the S channel or a sum of trajectories in the T channel, the dual descriptions, we would say. And there was a claim that it worked with some accuracy. Not very rigorous, not very precise at all, but it's a very interesting idea. What did it mean? Now, I remember clearly 50 years ago, just about today, when I attended my first conference ever. Yes, I just had graduated from, just got my PhD from Berkeley, and the ICHEP, the high energy, it used to be called the Rochester Conference, was held in Berkeley that year. And I was just, essentially a graduate student. So I went, like some of you, to learn about what was going on. And I heard a wonderful talk by Sergio Fubini, who said, with respect to this idea, what we need is not a pole, a resonance in the scattering amplitude. What we need is a Mandelstam pole. That term never survived. What he meant by that was we need some way of representing a scattering amplitude that contained both poles in the S channel, this channel, and poles in the T channel. Now, Fubini had a wonderful imagination. It was very inspiring, and he just said that in his summary talk at that meeting. And that inspired a bunch of people, including me. But it was, what did it mean, and how would you construct a Mandelstam pole? Well, Mandelstam proposed how to do this. That's why I regard him as the godfather of string theory. In 1967, the paper was published in the beginning of '68, but it was a preprint in the summer of '67, about a year later. He wrote a specific proposal for a dynamics based on rising REGGE trajectories, linear trajectories. So he made an approximation, as did Zohar today, that the scattering amplitude can be approximated by the contribution of a finite number of REGGE poles. Actually, you need an infinite number, of course. He assumed that the REGGE trajectories are straight lines, or equivalently, the scattering amplitude is dominated by narrow or stable particles, sharp resonances. Forget about the unitarity. Crossing is introduced by means of the generalized superconvergence relations due to E.G. and Horn and Schmidt, which sounds totally meaningless, but it is just the crossing symmetry, the duality I talked about. Then Levinson's theorem, etc. A very specific, this is just the abstract, very specific 10-page outline of how to go about constructing a Mandelstam pole. Essentially the assumptions that Zohar describe today in much more rigorous fashion. Well, I liked that idea, and I tried to construct it. So at the end of that year, bootstrap of the REGGE trajectory, within the dynamical scheme proposed by Mandelstam, rising REGGE trajectories, now resonance, generalized superconvergence relation is crossing symmetry. And try to do it for this channel, which has the advantage that the exchange particle is rho in all cyclic channels. Anyway, and even tried to do it for the vacuum, which would be the graviton amplitude. In today's terms, it didn't work. Anyway, I didn't solve the problem, but gamma functions began to occur. At the same time, there was another group in Israel, Adamello Rubinstein, Hector Rubinstein, Veneziano Virasoro, young postdocs at the Weizmann Institute, who essentially did the same thing with similar results. So this was the few people who were following Mandelstam's suggestion about how to construct a Mandelstam pole. But of course, what happened was that a few months later, Gabriele Veneziano, on a boat back home from the Weizmann Institute to Italy, discovered the beta function. And the rest is history. That's how string theory began. So Mandelstam deserves an enormous credit, in my opinion, for being the godfather of string theory. Okay. Now, of course, what we were trying to do back then was understand experimental high-energy physics, especially the strong interactions. Today, and theory was pretty impotent. You know, we saturated things with poles, Regge poles or poles. There was no real dynamics. The situation today is very different. The bottleneck in particle physics is experimental, not theoretical. We have tons of speculation, wonderful ideas, not much experimental evidence or clues. And we're all waiting to know whether, for example, the 750 GeV bump or fluctuation is real. Now, I've heard definitive opinions on this from many members of the audience who know for a fact, based on the publication of results in Facebook, that there is no particle there, but I would like to hear the experimenters say that. Or whatever else they're going to say in a few hours and the next few days. But, you know, we do have a problem. The problem is that the Planck scale, which Planck identified and the standard model confirms, appears to be the relevant scale where unification takes place, where strings are evident, et cetera, et cetera. And for theory, that's not really much of a problem, by and large, we can hope, because physics varies logarithmically from here, or from the LHC to the Planck scale, unless there are new thresholds, which we hope there might be, there should be. But by and large, variation of physics, physical phenomena, is logarithmic, which means that we can extrapolate over many orders of magnitude easily, because the logarithm is small. But the cost of exploring scales, higher energy scales, increases like a power, like the second power or worse in energy. And the disparity between this behavior of physics and this behavior of technology or of building instruments is a real problem. And we've been facing now for many years. That's one reason it's so important to do what we can to even go to a scale which is an order of magnitude greater than the LHC, like the Great Collider. But it's a fact of nature. We can't do anything about facts of nature. We have to figure out how to deal with them. So let's go to string theory, where theorists are unencumbered, can extrapolate, have no fewer constraints, at least until nature speaks her mind. So what is the state of string theory? What is string theory? Well, if you judge what string theory is by the content of Strings 2016, you might say string theory is mostly quantum field theory, which of course overlaps with particle physics and condensed matter physics and quantum information now and relativity and cosmology and, as always, math. And Nadi talked eloquently about the unity of physics and math and everything that we call, well, that's what we listened to this week, what we call string theory. So we can simply put everything in the bag, as Nadi did, and call this string theory. So I asked myself, is this a good term? If we consider strings 2xxx, where x might be any integer from 0 to 9, what are the x's, what is this going to be replaced when the x's become bigger than 0? Should we perhaps call this physics 2xxx? But even that's not enough. Well, that's misleading because most of physics is experimental physics. So maybe we should just call it fundamental physics. That's dangerous. It's politically loaded. Besides which, it doesn't contain mathematics and all computer science. Maybe all things fundamental. Well, that's a bit awkward. So I actually haven't been able to come up with a better name. So we might as well stick to strings. But we have to really understand what strings is. Now, I've made the point, and I'm sure some of you have heard me, but I'm going to reiterate that string theory, we don't know what it is, but even worse than that, it's not a theory. And I like to distinguish between a framework, a theory, and a model. Framework is something like classical mechanics, quantum mechanics, or quantum field theory, which is not a theory but a framework, and string theory, which is not a theory but a framework. A theory is something like Newton's or Einstein's theory of gravity, Maxwell's theory of E&M, or the Standard Model, which isn't a model, it's a theory. A theory is something specific. It might have some undetermined parameters or structure that you only know is true because that's the way nature works. But you can put its principles or its equations on a t-shirt, and given a few numbers, you can calculate, make predictions, disprove the theory, the Popperian sense. A model is not like the Standard Model. That's really a theory. A model is something like the BCS theory, should be a model, of superconductivity. In other words, you take a system of electrons or of atoms, and you make various approximations consistent with quantum mechanics and our knowledge of nuclei and atoms, and you keep the essence enough so that you can understand superconductivity. And if the model is bad, you made some errors, you don't change the theory, the Standard Model or non-relativistic quantum mechanics, you just, you correct your approximations. Beyond the Standard Model, models are models of quantum field theories that go beyond contain and go beyond the Standard Model. But string theory, I believe, belongs here, as does quantum field theory. They're frameworks. So more specifically, the general framework we have for physics nowadays is quantum mechanics, or specifically relativistic quantum mechanics, or quantum field theory. And within those frameworks, we have discovered, not derived, but taken from experiment, the particular quantum field theory within this framework that describes nature, as far as we can tell. And we call it the standard model, but it really is a theory. And within the standard model, there's my favorite theory, QCD, which has very few parameters, if any. And once you have a theory, then you can calculate. You can test with experiment, or you can calculate the spectrum of hadrons. So that's what you can do when you have a theory. You can disprove it in the Popperian sense, and that often happens, or you can calculate things you weren't able to calculate before. Now, in string theory, we don't have a theory, we have a framework. Not only that, this framework is not, in my opinion, separate or different than the framework that contains consistent quantum field theories. In fact, the stringy field theory framework contains just about all consistent field theories and stringy, brainy methods of calculating consistent semi-classical approximations to states in Hilbert space. And it appears including quantum gravity. It's an incredible framework, and we don't even understand the boundaries of this framework. We don't understand the boundaries of quantum field theory, to be honest. We understand low-energy quantum field theories, and we understand conformal fixed points, but once you start going to the UV, you need a bigger framework, and we have no idea what its extent is, what its structure is. That's what, by and large, people working in string theory are doing, is trying to understand this framework and control it. So, again, we have the framework of theoretical physics we've learned, especially since ADS-CFT, contains the quantum field theory framework and string theory, and has informed us that they're the same framework. But the question we face is, how do we get from this, the original goal of many of us who went from particle physics to string theory, the standard theory, the standard so-called model, and be in a position to calculate some of its properties that we can't so far, or explain some of its properties, and predict new phenomena. How do the forces unify? We have these hints that they unify the Planck scale together with gravity. That led us to string theory as a potential, now to be understood, enlargement of the framework. But we, I must say, are far from answering this question of unification. Now, I believe that there are three main issues, conceptual issues, problems, obstacles to solving this problem. And the first is the issue of uniqueness. Because what does it mean to unify the forces? It surely should be better than just find another gut quantum field theory or something like that that replaces the ugly SU, well, the SU1 times SU2 times SU3 standard theory. And string, 30 years ago, string theory methods seemed to offer that tantalizing hope of uniqueness. But that hope was soon dashed And uniqueness of a particular theory out of a large framework is not something that physics historically has been particularly able to do. Take the Standard Model. And why is it so difficult? Now it's regarded as infinitely worse, but I think it's always been the case. Now it's regarded that one string theory, or within the string framework, there are many theories, or many ways of constructing consistent quantum states in a systematic semi-classical approximation. They're called vacua. But there are in fact an infinite number of such things. But there were an infinite number of such things in the quantum field theory framework as well. I wonder whether this question isn't related to another question that is truly new and incredibly difficult, and for physics, fundamental, well, this question, what picks the theory from the framework, is not related to the question, again, that physics has avoided forever, namely the beginning and ending and end of time. What happens at the Big Bang, or at the big something at the end? And the question of how the universe began, or what the initial condition of cosmology is a question physics, again, has avoided forever, hasn't had to address, doesn't want to address, assumes it's not important for predicting the results of experiments we set up yesterday and measure tomorrow. But when we're asking about the uniqueness of the particular theory in a big framework, it's not obvious that this isn't relevant, especially as Einstein taught us, the answer to any question that involves dynamical space-time, the answer is a history of space-time which contains a beginning, a boundary, if there is one, and an end. And it's not clear that any so-called vacuum or solution or method for constructing consistent quantum states makes any sense at all if it has singular beginnings or weird ends. And here, we certainly don't know what the rules are, since physics has always avoided this issue. And finally, we've learned, and including the dynamics of space-time and quantum gravity, that our very notions of the most fundamental concept we possess, that of space and time, are shaky. And that is clearly connected to our understanding, perhaps, of the answer to this question and this one. Space-time appears to be best thought of as an emergent concept, as well as gravity in a sense. And again, we have no understanding of what it would truly mean to formulate a priori the rules of what physics is and how you do physics without an a priori space-time, or at least time. So, we have fantastic instruments and experiments, and future experiments. We have fantastic speculations. And I truly believe the best is yet to come. I only hope it comes quick. But meanwhile, next year, as we say in Tel Aviv, this is the poster of the Strings 2017, which will be held in Tel Aviv at the end of June, as Zohar announced. And I hope to see you all there. Strings 2018, as Hiroshi announced, will be in Okinawa, in Japan, and Strings 2019 is planned to be in Brussels. And we will see afterwards. So, thanks. Thanks to our hosts, S.D. Yao, who isn't here, but I'll thank him personally, and Shikun Tsu, which I'm mispronouncing, I'm sure, who was our vice president of Tsinghua University and has been so welcoming, and to Hong Jian He, and of course to the organizers, and especially to Li Si and to Song Wei, who have done an incredible job and have worked so hard to make this a wonderful conference, and to the administrative staff and the small army of students who have seen after our needs and taken care of us. Thanks to everyone and to all of you.
Anyway, let's all give a big round of applause to David too. We can take a few questions or comments, dissenting comments.
Comments would be appreciated.
Nadi's hand is up. We can't hear you.
Can't hear a thing.
This was a beautiful talk, of course, but there's something that's kind of puzzling. You made this distinction between framework, theory, and model, which is nice.
No. Now, what I mean, I'll give you an example, okay? Let's take Einstein's theory of gravity, okay? It is a classical field theory, right? That's a framework. Local fields, partial PDEs, second order time derivatives, okay? All those things, Einstein was working in that framework. Now, he added a principle, which is what we usually do, a principle or a symmetry. His principle was a symmetry principle. And then, uniquely, we would say today, up to higher, effective field theory, he understood that. He never believed it was the final story. He knew it was just the lowest order term with the cosmological constant of an effective field theory. He had a principle, actually, that didn't allow higher derivative terms. But with that principle, he picked out of that general framework of classical field theory, which is by and large untestable unless you have a particular theory. He picked out of that framework a particular classical field theory, which was generally covariant. Okay? Now, to some extent, the belief, the hope, 30 years ago was that string theory was constrained enough, was constrained enough that perhaps with some little bit of extra principle or none, it was unique. That, as I said, was rapidly shattered. And to think of something, you might then ask, well, where does Einstein's principle come from? That of general covariance? Einstein would have answered you, you got to assume something, right? But he was very proud of the fact that given the framework and the added symmetry, and ignoring the lambda term. He had essentially no parameters, as long as you don't put in matter, which he tried to then derive. No parameters, just a scale. That's what I mean, okay? The standard model is not of that type. We have no principle that picks out the gauge group. Just the fact that we need that particular gauge group to agree with what we observe. We have no principle to pick out the matter content. Well, you know, anomaly cancellation, but given no principle that picks out how many families there are or what the representation is, as you know, just observation. We have no principle that picks out the masses of the, or the Higgs couplings, or the masses of the quarks and leptons. We just have to measure them. People have tried, as you know very well, over the years to find principles or symmetries or something, lack of anomalies or something that would constrain maybe to as much as possible, and haven't. And that probably, I think you probably agree that within the standard quantum field theory framework, we're not likely to find such a principle. Maybe you disagree, but that's the kind of thing you would look for to pick out a theory you can measure, test, calculate from a framework which is very hard to test. You know, it's very hard to test quantum field theory. Dispersion relation, very hard to find general tests. CPT is the best example, but they're very, to really make progress, you need a theory.
Any more comments? Or? Okay, this is the hand over there.
David, thank you for the wonderful lecture. I have a question with regard to one of your slides, whereby you pointed out that a correlation between energy scale and the amount of effort to obtain results, either in theory or in experiment. I suppose in the experimental case, there could be some empirical evidence to suggest that the scale like energy squared. I'm curious how you would draw the conclusion that on the theoretical side, you can extrapolate that, you know, the scales like not energy. Thank you.
Well, I'm just using our best tool, the standard model. So, for example, where is it? For example, you know, here's an extrapolation that was done almost 30 years ago. And this is the limit of observation, LHC. And we extrapolate the forces. Now, you can't extrapolate what you haven't seen. So there could be, and we hope supersymmetry is a threshold which we can't extrapolate, obviously, something that is zero and then turns on. But what we really know about is these forces, described by the standard theory and the Higgs sector as well. And you know, we're theorists, we can extrapolate. Now, nobody would believe us if it wasn't a logarithmic variation over 14, 15 orders of magnitude. But it is. And so nothing much happens until you get to this point here, right, where what's happening? Why don't I? Where gravity comes in. That's also an extrapolation, by the way. Gravity does not vary logarithmically. It varies like a power. the charge of gravity is energy itself, so gravity varies like energy squared, just like the cost of accelerators. But it starts out so weak that it's irrelevant until you get to this scale. So this, for me, by the way, is the most important clue we have. But for progress, it's a nightmare. So actually here we have plotted physics of the standard model, varying very slowly, and this is the cost of accelerators. And this is an increase from here to here, the force of gravity, by 40 orders of magnitude. So that's a challenge.
We can take one more comment if the US hand is up.
Maybe slightly happier note, at least in early universe cosmology, the higher the energy scale it is, the easier it is to see.
Right. Yes. Thanks Eva for reminding me, because I was going to make a comment. Yes. Unfortunately, well, okay. That's true, and we hope for the best.
Okay, well, let's thank David again. I think let's thank the organizers one more time for a great